Hello, my name is Zachary James Davis. I am the coordinator of the European project LEBED. LEBED is the development of materials and processes for lightweight embedded electronics. I'm also a team manager at the Danish Technological Institute, working within printed and embedded electronics for over 5 to 10 years. First of all, I just want to say a little bit about what is LEBED and how can it help you. Today, we're also going to discuss some of the cases, the end user cases that we have performed in LEBED. So what can LEBED help with? Well, if you want to add electronic functionalities into your existing products or new products that are coming on, that you would like to come on the market, that will communicate with electronics, that can either sense the environment using temperature, humidity, movement, etc., or incorporate lighting in a more embedded and lightweight manner. This is how we can help you. At the same time, we can integrate these in a very seamless way. We can add by printing onto foils, we can then embed them into different materials. We can also make them quite transparent and invisible. So really be able to add these functionalities in a very sort of seamless way. Finally, we can also reduce production costs compared to standard electronics. So electronics is using typically etching, deposition and etching technologies, rigid boards. What we can do in this case is to reduce both the production waste, the material costs, and also energy consumption by using printing technologies instead of etching and lithography. Finally, we can also complete the value chain inside of Europe instead of going outside of Europe, which is extremely important in these times. The sort of essence of LEBED is also the structure of LEBED is as follows. We have the single entry point, and the single entry point is where you as a customer can come in and get access to LEBED services and infrastructure. We have 3 phases in LEBED. The first phase is a techno-economic modeling phase where we can help companies with services, both technical but also non-technical services, assess the ideas and what technologies can be used, do some sort of preliminary calculations on economics, how this will save money, life cycle assessment. We can also provide patent mapping. That means finding out who is doing what in the world, if there's IPR already existing on that idea, and we can also help the customers get funding if that's needed. Then when this is usually done, we go to a pilot project phase where we actually get access to infrastructure. We have, of course, run several of these pilot projects, and we'll show some of the results today. And then finally, we actually can also help you transfer the knowledge going on to the next step. That means either going to market or applying for funding or getting investments to the next stage of the project in your project. So the first one I want to show is the interactive lighting demo, and this is done together with Swarovski. So Swarovski, they are making crystal ornaments, and they've been doing this for decades. But they are really wanting to push their technology into the future. So having sort of interactive. So what they have asked us to do is a few things, and one of them was, can we make an interactive surface using their crystals? So that they gave us these images you see on the left-hand side, where you have a huge array of crystals, and you touch it and it lights up and does the specific things. You can also use that for wearables. So if you want to have a dress or a costume that has lighting embedded and using their crystals as well, this is some of the things that can be done. In the end, what we was able to do is do a sort of, I would say, not just a proof of concept, but a first rudimentary prototype, which you see on the left. So we made a 4x4 array, and we embedded both touch sensing elements and LED lighting elements on the same printed foil, and this is on a PET foil. And then we mounted on top of that the crystals. And then, of course, we programmed it up. We put that into a microcontroller, and then program it for doing interaction, you see on the video. The way we did that was by printing using a screen print process on a cheap polymer PET foil, and we're printing both silver and dielectric materials in 2 or 3 layers in order to build up both the touch sensing elements, which are the blue and green layers, and the LED, which is the black and red elements here. And these are done by printing of silver and dielectric on PET foils. Next one we had was the interactive decorative, which was in transparent. So what they really wanted for us is to go fully transparent. So we in this case we had to really think about this, because normally printing of conductive tracks is done through printing of silver, and silver is not transparent at all. As you can see in the previous, you could actually see some of the printed lines on the foil. But what they really wanted is to okay, can we make touch interaction and lighting on a fully transparent foil? And this is actually the end result. You can see this is the foil on that we have made, which has both touch interaction and LED lighting. In order to do that, we had to really understand how to do this. So what we did was developed silver nanowire based inks, and the silver nanowires are actually these really long, as you can see on the right hand side, high aspect ratio conductive wires, and the nanometer range in diameter. So the idea is that you have these spread out across the film, and they are touching, of course, so they are conducting electricity, but when you look at it, they are smaller than the wavelength of light, and thus basically transparent. So what we were able to do is make actually a transparent ink and then coat it onto the substrate, which has quite a high conductivity and also a high transparency, around 90% transparency. There is a small video here we could show. Turn down which is actually the wrong video. But then we will go to the next video. This is this one. I'm sorry about that. So this is the interaction. So this is the touch interaction. He's touching actually 3 different areas, and each area does a different lighting experience. So just to show you that we have both the touch interaction and the LED lighting in one package. The next case I want to show you is Acciona. Acciona is a large construction company in Spain, which is actually has quite a lot of different activities, and one of the activities is making fiber and carbon-based composites using what we call a protrusion process. And this is what you see in the image here, is this protrusion process line where they make big elements, big objects out of fiberglass composites and also carbon-based composites. So what they were really asking for in this case was to monitor both the temperature and during the protrusion. So having a sort of a thin, flexible electronic foil that actually had temperature logging, and then to put that into the protrusion process. That was the first thing they wanted. And the other thing they wanted was to be able to have these embedded into their composites, and then when we put them into a construction, it could be a windmill or a lighthouse or something else, that we can use that to monitor both the so the temperature and humidity over time that has been absorbed into the composite materials. So this is the main challenge is finding the lubrication hardware that could survive the high temperature and corrosive conditions, because putting them into this so when this is the protrusion process itself has high temperature, high pressure, and also has some volatile chemicals. So this to actually make an electronic that can survive that was quite a challenge. But it actually was quite. In the end, we did find the right material set in order to be able to protect the electronics, so they didn't break during the protrusion process. So the solution was it enables the data, reliable data for optimizing their own protrusion process in the end. Right now, we can also see we have done this sort of the initial results for the protrusion process, but also have them embedded in several devices, which you can see here on the right-hand side, where they are just sitting in the Porta della Vendita Valencia, sorry, and are being sort of measured every once in a while to understand what is the long-term environment, sort of robustness of these devices. And so far, we have not seen any signs of a degradation over a period of over 6 months. So this is really, really good results for us, that we can actually have the embedded sensors in the composites out in the field, and this is actually very close to very harsh, high humidity, temperature variations, etc., and things are working quite well. Final end user case I want to talk about is in-mold electronics for automotive applications. This is together with the Meyer, which is a Italian company working with embedding of electronics into injection molded parts. So they have injection molding. They are experts in injection molding. And what we were able to do is they are giving us some concepts. This is the part which is inside the car, which has some, and they would like to have a large display area, and they want to have touch interaction and some holes here for the sort of ventilation, and they want to have some be able to make that into plastic, and then they can put that. But instead of having these sort of buttons that are mechanical, they want to have touch interaction and lighting inside the plastic part. So there's LED lighting and there's touch interaction. So this is the foil that was developed through the Libed Consortium, which actually has a lot of LEDs on the peripheral and also 4 touch interaction areas. And then on top of that, we actually did add all of the sort of electronics, the control electronics into the part as well. So we have both the control electronics, LED lighting, and touch interaction in one foil. This is sort of the end user. This is actually the foil before injection molding. You can see that you're touching and then it's lighting up. And this is actually after the injection molding process. In this case, we used a sort of a semi-transparent in order to be able to see the electronics, but to give us a nice feel of how it looked. And you can see it's actually working quite well. So we're able to embed this foil into the injection mold, overmold it, and it was surviving. And it was actually quite a test. It didn't work the first time. Actually, it actually took several iterations, to really understand the high pressures and temperatures involved that were actually, displacing some of the mounted components. But in this case, we're able to really solve these issues and bring a nice product to Meyer, a nice process as well. That's actually all that we have for the sort of the cases so far. We're still working quite a lot on new cases. We're also working into more with some more stretchable textile integration as well. But these are things that are still in progress and maybe will come in a later presentation. So if you want to follow Libed, you can please do so. We have LinkedIn and Twitter, and then I would also like to thank all of the partners that are involved in all of these nice results. We are really a dedicated group that is working really, trying to really help industry implement these sort of printing materials and processes in order to make functional electronics in everyday products. So with that, I would say thank you, and yeah, come visit us at the website.